All right, so all of you know that the cryptography is a lot of mathematics, right? And so some of that math will be in the today's lecture, right? There is not a lot of math in this course as such because we are course on network security, but for cryptography part we need some math part, right? So that math is today. So today we will talk about how to do GCD. Everybody knows what is GCD? Greatest common something? Huh? Okay, greatest common denominator or greatest common divisor. Okay, so the same thing. And then we talk about modular arithmetic, and most of you should know mod 2 arithmetic, how to add things mod 2. Then we get into things which are called groups, rings and fields and Galois fields. You know, that basically about those and how to do polynomial arithmetic. All of this is from chapter 4 of the book. So first of all, GCD, greatest common divisor. He said greatest common denominator. I think that would probably work as well. But to find GCD, you have to find out, for example, what is the biggest number, greatest number that will divide both 10 and 25. In this case, that number is 5. In this example, right? How do you find 5? Well, you could factorize both of them and then find out what is the common factors and then multiply them. But that's actually much more difficult than the method here, which is that you divide 25 by 10. Whatever remainder comes out, you divide that by, basically you keep, so you divide 10 by 25, you got 5. You divide 5 into 10 basically, and then you get 2 and you got 0. Once you get a 0, then the last divisor is the greatest common divisor. So how many people have done this kind of before, division, GCD? Raise your hand a little bit more, higher. Okay, so you have done it. How many people have never done this kind of thing, or seeing for the first time? 2, 3, 4, 5. Okay, this is actually should have been taught in high school. All right, so I'm not going to go into this, but if you have not seen this, you might want to practice the division. Okay, so this is straightforward. The principle is not very difficult. All you have to do is take a number, bigger number, divide by the smaller number, whatever remainder comes out, divide into the previous divisor, and you keep doing this. This is not necessary that it will finish in two rounds. You might need, many rounds. The important thing is whenever you get the 0 as a remainder, then the previous divisor is the greatest common divisor. This is called the Euclid's algorithm. Okay? However, there is a tabular method of doing the same thing, and so this tabular method requires 4 columns. They are labeled Q for quotient, R for remainder, U and V are the coefficient, and then we want to find out the greatest common divisor of 10 and 25. Now this you may not have done before, so please listen carefully. Even if you have done GCD by division before, you may not have done the tabular method, right? So listen carefully. And the first 2 lines are filled in by yourself. So the first line you write the bigger number, which in this case is 25, and then you write down 0, 1 and 0 here. What this means is whatever is in the remainder column, if you multiply that to U and V, you should get equal to, if you multiply UI, this number with this coefficient, and 10 with this coefficient, then you should get Ri. Every single row that will be true. But for the first row this is true. If I take 25, multiply by 1, take 10, multiply by 0, add the 2, how much I get? 25. The second row we write down the similar thing, 0 and 10, the second lower number, and then we write down 1, 0. here rather than 0, 1 here. So 1, 0. So now this thing that we talked about is true, because you take 25 multiplied by 0, 10 multiplied by 1, you add them together, you get a 10. Right? Once you have written those two rows, the third row, the way you write the third row is that first you divide this last row, which in this case is right now second row, into the previous row. So 10 you divide into 25. When 25 is divided by 10, you get a quotient of 2 and a remainder of 5. Now, so these two things you could do. Now, once you take 2, then you do the same thing basically in other columns like you did in this column. You multiply 2 to this number, 2 times 1, and subtract from the previous number. That's what actually you did for the remainder here. What you did was you take 2 times 20 and you subtracted from 25 to get a 5. Right? Similarly, you do on this column. 2 times 1, subtract from 0, you get a minus 2. 2 times 0 is 0, and subtracted from 1 is 1. Now, that property still holds. If you take 1 times 25 minus 2 times 10, you get a 5. Right? Ri is always equal to ui times xi plus vi times yi. If this is x and y. Ui times x plus actually. Ri is always equal to ui times x plus vi times y. So this is correct calculation, right? Now what we do is we take this last value 5, divide into 10 and get the quotient, which is 0. That's why just quotient is 2. Right? Now we do the same thing. We multiply 5 by 2, subtract from 10, we get a 0. We multiply 2 with minus 2, how much we get? Minus 4, subtract from 1, we get plus 5. Right? We take 2, multiply by 1, this plus 2, subtract from 0, we get a minus 2. Alright? The good news is that the remainder is 0. Once the remainder is 0, your process is done. At that point, the previous number is the GCD, 5, is the greatest common divisor. Okay? In addition, the advantage of doing this tabular method is now that we can write down equations like this, where 0 equal to 5 times x plus minus 2 times y. Right? However, if this last number was not 0, suppose it was 1 by some chance, and we will see an example where it is 1. If this is 1, last number is 1, then you can write down that uix plus viy equal to 1. And by the way, that means that the GCD is 1, which means that they are relatively prime. Relatively prime means the greatest common divisor is 1, means there is no number that divides both of them. Right? So that is one thing, but also you know that this is equal to 1. So what this means is that if you were working on mod y arithmetic, then ui would be the inverse of x, because only when you multiply a number with its inverse you get a 1. Right? In the mod y arithmetic, this is all 0 anyway, because any multiple of y is 0. Right? When you have mod 5 arithmetics, 5 is 0, 10 is 0, 20, 15 is 0. So, right? The numbers are only from 0 through 4. So basically that allows you to get an inverse by this method, and there are many places in the course where we will need the inverse. So the only way to get inverse is to do this Euclid's algorithm in a tabular form. Alright? And here is the procedure. Exactly the steps that we did, I wrote it down here. Can everybody do this table? If you have a question as to how we got any number in here, please ask right now. All right, if you can, then I would like you to fill in this table right now. And if you want, you can always go back in your handout to the procedure, just in case if you're not sure what to do. You can go back to previous slide and look at the method and do it. So this is not an exam or anything like that. I just want to make sure that you can write the rows. Yeah.
It's supposed to be 12 and 105 there, 'cause I thought you said the remaining.
Oh, yeah, right. Good point. So I am asking for the GCD of 12 and 105. So why did I put 8 there? Okay, you have to change one of the two numbers, either 12 or 8. Let's just do, for the sake of it, let's just do 8 both places.
15 or 105.
And let's do 15, just to keep it simple. All right. So I'm going to fix that. So this is, how do I fix it? Oh, it's not very easy to fix it right now. Oh no, I wouldn't do it. So, okay, I can fix it. This is 8 and this is 15. You're done? Okay. All right, if everybody is done, what is the GCD? Huh? 1, the greatest common. They are relatively prime, right? So we can write down, okay, so the question is what is the last row that you have? And I need to write down the last row. So what is the left for the last row? Anybody? Go ahead. 0.
No, 7, 0, negative 15.
7, 0 even. 7, 0?
Yeah, 7, 0, negative 15, 8.
Negative what?
Negative 15 and
15 and then plus, yeah,
8.
8. Before that, what was the row?
1, 1, 2, negative 1.
Okay, so this row is important. Because what this is saying is that 2 times 8 minus 1 times 15 equal to 1. Right? 2 times 8 minus 15, 16 minus 15 is 1, which is correct, right? But it is also saying that if we were to do in mod 15 arithmetic, then 2 is equal to 8 raised to minus 1. Inverse of 8 is 2. Alright? So if you were to find out 1 upon 8, 1 upon 8 is equal to 2, because whatever the inverse of 8 is, when you multiply that with 8, you get a 1. So this number is important. This 2 is important to note. Okay? Alright. So now the homework. Find the multiplicative inverse of 5678 mod 8765. Alright. Now first I had given it as a homework, but then I thought that it's just too much for us to check it out. So I am not going to check it out. You just do it on your own, and here's the answer. You can do it at home, you can do it now, it doesn't matter, but let's move on. Okay? So everybody can do that, right? Basically these are the two numbers you write down in the table and do the same table that you did a minute ago. Right? And if you don't get a 1, then there is no multiplicative inverse, then that's a problem. But if you hopefully will get a 1, they might be relatively prime, and you will get the inverse. And the answer is 2527. Okay? So you don't have to submit that one. Oh, by the way, in your handout, this red line does not appear. So please write it down. Homework 4A is not due. Okay? Alright, now let's talk about modular arithmetic a little bit more. Modular arithmetic works almost like the regular arithmetic, except that all the numbers are less than the module, basically the base or whatever you want to call it. So this is the arithmetic mod m. If you want to do x times y mod m, you can do x mod m times y mod m, and then whole thing mod m. Right? When you want to do addition mod m, you could do x mod m, where x could be much larger than a number than m, and then y could be much larger than m. First you reduce them to less than m, then you add them, and if there is more than m, then you again do mod m. Right? If they are less than m, then that's fine. Similarly, you can do x minus y. You can do powers x raised to 4. If you want to do x raised to 4, you can do x raised to 2 and x raised to 2. And both of them then do mod first, and then you do mod on the product. If you want to do x raised to I times j, you can do x raised to I and then raise the whole thing to j. So here's some examples. 125 mod 187 is what? 125, because it is less than 187, right? But what about 225 plus 285 mod 187? We do it in pieces. First, we reduce 225 to mod 87, and then we reduce 285 to mod 87. So this gives you 38, this gives you 98. Then we add, which is 136, which is less than 187, so that's all we set. You're all set. We want to do 125 square. We do the square, we find out is 15,625. We reduce it by 187, we get it 104. Right? We want to do 125 raised to 4. Now, you really don't want to do this first. Basically, what you do is you want to do it square first and then square it later. So first you do the square and you get 104. Then you square the 104. Okay, then you get 10,000 and you do mod now and you get 157. So that is 1 raised to 10 raised to 4. If you want to get a 6, you could do 4 and 2. And so 4 is 157, 6 is 104, and so the total is easy to calculate, and you get 59. Does everybody feel comfortable with the division, multiplication, powers and all that in mod? Okay. All right. If you do, so let's just see. Set of all integers is G. So when we have minus infinity to plus infinity, every integer including 0, that we call Z. When we say Z sub n, we mean set of all non-negative integers less than n, which means 0 through n minus 1. So G sub 2 is 0, 1. G sub 8 is 0, 1, 2, 3, 4, 5, 6, 7. All right? And now you can do all the arithmetic, subtraction, multiplication, addition, division, and all the answers will be in the same set. So regardless of which two numbers you take, you multiply them, they will be in this set. The result will be in this set. Right? So for example, 5 plus 7 mod 8 in Z8, 5 plus 7 mod 8 is 4, 4 minus 5 mod 8. How much is 4 minus 5? Minus 1 you get first, but then 8 is equal to 0, so you can just add 8. Whenever you get into negative territory, you can add 8. Whenever you get into territory which is more than 8, you subtract 8. Right? So in this case it is minus 1, so we add 8, we get 7. 5 times 7 is 35, mod 8 we divide by 8 and we know that 32, and then subtract 32 you get 3. 3 times 7, that's interesting. How do you do 3 divided by 7? 3 divided by 7, how do you do that one? Well, first of all, you have to find the inverse of 7. Right? 1 upon 7 like we talked about here. So what is the inverse of 7 in this? What is the number that I multiply to 7 so I can get 1? So we say, okay, 7, 14. So 21, 7 times 3 is 21, and we kind of keep dividing by 8. We don't get, when we divide 21 by 8, we don't get 1. 28, 35, after that we have 42, we get a 2, plus 7, 49, we get a 1. 7 times 7 is 49, which mod 8 is 1. So what is the inverse of 7? 7 itself. Remember, since 7 times 7 is equal to 1, 1 upon 7 is equal to 7. Right? Make sense? In mod 8 arithmetic, 7 times 7 is equal to 49 equal to 1, right? Forget the 49 part. 7 times 7 equal to 1, so 1 upon 7 equal to 7. So that means the inverse of 7 is 7, you multiply it to 3, you get 21, and then you do mod 8, you get 5. Okay? What is 5 times 5? That's to be trivial. 5 times 5 is 25, mod 8 is 1. So now the inverse of 5 is also 5. By the way, you can sit down and write the inverse of all of them. It's not that the inverse of number is the same number. For example, just for the sake of it, what is the inverse of 2? You won't find it. Actually, it doesn't exist. So, I mean, that could be a problem in this case. There is no multiple of 2 which will be 1 more than 8. Multiple of 8. Right? So So in this has to be organized slightly differently, right? Okay. All right. So some numbers. So in this particular case, some inverses exist, some inverses do not exist, and we will talk about that as to when they don't exist, what do we do. All right. So modular arithmetic, you can do the addition, and that is addition is commutative. So w plus x is same as x plus w. W times x is same as x times w. Associative, you can do anything first. You can do w plus x and then you do the y, or you can do w first and x plus, first you do x plus y and then do w later. Right? Similarly for multiplication. They are distributive in the sense that the multiplication distributes over addition. So when you do w times x plus y, you could do w times x plus w times y. Remember, this is only multiplication distributes over addition, not the addition does not distribute over multiplication. There are identities. Identities means that there is an additive identity which is 0. When you add 0, the number doesn't change. When you multiply by 1, the number doesn't change. So 1 is the multiplicative identity, 0 is the additive identity. And there could be additive inverse. When there is an additive inverse, basically the sum is 0, and multiplicative inverse, the product is 1. Or actually in both cases, the result of the operation is equal to the identity. Alright. So now the homework, again you don't have to submit, and please write down what is in the red here, is that determine 128 raised to 107 mod 187. Now wrong thing would be to put that thing in the Excel and hope that it will come out right, because it will all overflow and you will get the wrong answer without Excel telling you that. Maybe it will tell you that overflow, but if you just do like that, there will be a problem. So what you need to do is, you need to do in pieces. First of all, you have to know that 107 is 64 plus 32 plus something something, and to get to 128, sorry, there is a mistake here. 125 raised to something. Come on. This should be 125. So you start with 125 square, then the power of 4, then you go to power of 8, then you go to power of, and every time the number should be less than 187. Right? You can go to 8, 16, 32, 64, and then you add up the appropriate powers to get 107. Multiply the numbers. And in every multiplication, you should make sure that the number is less than 187. That way, nothing overflows. Everything is integer arithmetic, and you get the answer 5. If you do a mistake, your encryption scheme will not work. We are going to use all this in encryption later on. Okay, so everybody can do this? Okay. Now, the mathematicians have come up with some names that probably are not that difficult to understand, but probably you didn't hear those names before, so I'm going to just explain to you those names, and from now on we can use them in the course. Most of the common thing that will be used in this course is Galois field, GF. To get to Galois field, we have to start from the group. So a group is any element, any set that is closed with respect to some operation. And closed means that the result of the operation is also in this set. So for example, and the operation we can call dot, we don't know what dot is, but if we do A dot B dot C, it is associative. That means operation can be done in any order. It has an identity. So there is a E which when the operation is done, it remains the same thing, has an inverse, and so on and so forth. And if, so this is any such thing is a group. And we already saw a group before a minute ago. Right? But there are other groups which don't have to be numbers, this could be just ABCDs. The operations don't have to be addition, multiplication, there could be some operation. Alright? If the operation is commutative, which is not necessary, if it is commutative, then it is called an abelian group. Abelian group. Alright? So for example, subtraction is not commutative. So you will not use any set with subtraction, and I mean it won't be a abelian group with respect to subtraction. Right? But it could be abelian with respect to addition, multiplication and all that. Now Z8, the group that we saw a minute ago, is a group with respect to modular addition, and the identity is 0. We noticed that it was not a group with respect to multiplication because there was no identity. Oh, because inverses, the third property was violated. There were no inverses. All right. And you can apply the operator many times. So if you apply the operator 3 times, we could call it cube. And if every element is a power of some fixed element, then we call it a cyclic group. Now this is important, is that suppose you have a set which has 8 numbers or 8 elements, and every element is power of some number. Then that is a cyclic group. So not every group is a cyclic group. Okay? So let me give you an example of a cyclic group. All right. So I just added 0 there. I think 0 has to be there. But basically, if you had taken 1, 2, 4, 8, all of these can be generated from 2. So 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8. And this is a group for multiplication, mod 12 multiplication. So when you multiply, the result comes out in the same group. But this, all the members can be generated from one element 2. Yeah.
Even though you can't generate 0?
Yeah, see, the thing is, 0 somehow, and I've seen, this is I was not for sure, but I've seen in all the examples worked out everywhere, 0 is somehow given as exception, where exception basically 0 is a power of 2 actually. I mean, if you really think about it, it's minus infinity. But and you multiply 0 with everything else, the result is in 0 here, so that it satisfies all of that property except for what is the power of 2, and so there is a power of 2 which is 0. Right? So the whole group satisfies the property that we talked about. Alright, so this is a cyclic group. Look, this is a mod 12, this is a cyclic group with mod 12 multiplication. So when we talk about mod 12 multiplication, in this group only, right? So we are not talking about number 11 here because that is not a member of the set. A ring. So some groups are ring. Which groups are ring? The rings have 2 operations which can be called addition and multiplication. The group has to be abelian with respect to addition, and the multiplication have to be associative, and the multiplication has to be distributive. So we have seen all of this. So everything that we saw before, like mod, not in mod 8, but we saw it in the mod 2, arithmetic for example, that was all a ring. Those were rings, right? And then if the multiplication is commutative, then that is a commutative ring. And if the multiplication has an identity and no 0 divisors, then it is an integral domain. Alright? So basically, more and more restrictions you put, you get a smaller set of such groups and they get a name. And if you need to know more about all of this, Wikipedia again tells you a little bit better and easier than the book. Alright, so here's the homework. This you have to submit. So here is a set. It has 3 elements A, B, C, and the plus operation is defined as in the table. And the multiplication operation is defined as in the table. Now you have to verify that all those conditions are satisfied for the ring or not. Is S a ring? So you have to see whether obviously you see that this summation, it is closed with respect to summation because the result of the summation is in the set, and it is closed with multiplication because the result of the multiplication is in the set. The question is whether all of these other things are true. A plus B is equal to B plus A. Is it commutative? Whether this is associative, whether this is distributed, and all that. Right? So you write down 5 conditions and write down whether this is true or not. If one comes out false, the answer is no. If all of them are true, the answer is yes. But you have to write down all the conditions and show that those are true. This is problem number 4.3 from the book. So far what we have done is, we are going to get to the last thing, which is called a field. A field is an integral domain in which each element has a multiplicative inverse. So the important thing about the field is now we need an inverse. So we saw an example of a set which was not a field. Anybody remembers what was that set? Does anyone remember a set? Yeah.
It had 2 in it.
Z8. Z8 didn't have a ring, didn't have the inverse of 2. So if the inverse exists, then we call it a field. So here are the set of properties. If it is closed, associative, additive identity, and additive inverse, we call it a group. If it is commutative, we call it a abelian group. If it is closed under multiplication and associativity of multiplication distributive law, then this is a ring. If it is commutative multiplication, it is a commutative ring. If multiplicative identity exists and no zero divisors, then it is integral domain. If it is a multiplicative inverse, then it is a field. Alright, keep this picture in front of you. Whenever you have to test out whether it is a ring or a group or a field or what, So this is all the sets, properties that we need. 1, 2, 3, 4, 5, and 7. 12 properties. So the final thing, we reach the final thing that we want to reach is the Galois field. Galois field actually are also called finite fields. Finite field means finite. It means they're not infinite. The number of elements is not infinite. Finite fields. And a field with a finite number of elements is called finite field, and it is also called Galois field. And generally written as GF with the number of elements inside it, which generally has to be a power. If it is a field, it will always be a power of a prime, p raised to n. P is a prime, n is some number. If it is not a prime raised to n, p raised to n, it is not a Galois field because it will not satisfy one of those properties. So the number of elements is always a power of a prime number. So if n equal to 1, then g of p is a set of integer with arithmetic operation modulo prime p, can do addition, subtraction, multiplication, and division without leaving the field g of p. If it is a field, then you can do all of these operations. G of 2 is basically has 2 members, 0 and 1, and you can do everything, multiplication, addition, subtraction, and the result will come out 0 or 1. G of 8, would be mod 8 arithmetic, but you have to define that carefully, as we will show you in a few examples later on, not just the way we did it, okay? There is no g of 6 because 6 is not a power of a prime. Okay? So here g of 7 is actually straight mod 7. So in g of 7, if you take, these are the 6 elements, the product is defined as a standard method. Everything times 0 is 0, everything times 1 is the same number, everything times 2 is whatever number, like that. You can define straightforward way, and you could have done the addition and everything else. So g of 7 is a Galois field. Now the things become a little bit more complicated. So far we were talking about numbers. Now we will talk about polynomials. So any polynomial can be written as a power of x. So this is a polynomial of order n, because the highest coefficient which is non-zero is x raised to n. And now you know, all of you should know, and I'm not going to teach you here how to add, subtract and multiply polynomials as usual, right? That is something taught in the algebra, again in high school. So I assume that you know that part, and you can find the remainders and the quotient. Yeah.
So for the Galois field of 8, does 2 just not exist as a...
Not a straightforward mod 8 arithmetic, but we have an example coming up where we can do it with the polynomials. So it will come up back in polynomials. So some polynomials have no factors and therefore they are prime polynomials. You know how to factorize a polynomial, and if you cannot find a factor, then that's a prime polynomial. So polynomials have the same properties that the numbers have. And so that is the normal arithmetic that is taught in high school. What is not taught in high school is probably the polynomial arithmetic with mod p coefficient. Mod p coefficient means they probably don't teach you how to do mod 8 or mod 7 or mod 3 or 2, polynomials. And that we will teach you here. The next step would be to teach you mod p coefficient but mod mx operation. So the coefficient will be mod, say for example 8, coefficient could be mod 8. So coefficient would be between from 0 to 7, but really the whole polynomial thing we do with mod mx, with some other polynomial. So let's do mod 2 coefficients. So here is an example of a polynomial which has mod 2 coefficient, only 0 or 1. So we can call it x cubed plus x square, and the coefficient of x is 0, coefficient of 1 is 0. Right? The coefficient of only 2 terms is 1. And gx is another polynomial. In this case it is a polynomial of degree 2, and all the coefficients are non-zero. If you were to add these two, what will you get? X cubed, you get that. Now x square is here plus x square is here. How much you get? 2x square. 2x square is same as 0x square. 2 is same as 0. Right? Either you think that way or you think in terms of exclusive R. So 1 exclusive R1 is 0. For at least for mod 2, the exclusive R is a good way to think. Okay. Anyway, so you got 0x square plus 1x plus 1. That's the sum. Multiplication. Now this one, to do this, you really have to do long multiplication. So how do you do long multiplication? Everybody knows how to do long multiplication. Let's just do that one. So we want to multiply fx by gx. So x square, x cubed plus x square. We want to multiply by x square plus x plus 1. First we multiply by x square. We get x5 plus x raised to 4 Then we multiply by x, so we get x4 plus x3. Then we multiply by 1, we get x3 plus x squared. Then we add up all of these, we get how much? x5 we get x5 plus nothing here, right? Plus nothing here, plus x squared. So you can get that fx times gx is x5 plus x squared. You want to divide, you can do the division same way. You could divide and then you could get a quotient and a remainder. Remainder would be less than the divisor basically in degrees, right? As long as the degree is higher than the divisor, you keep dividing until you get a remainder. And so Rx is the remainder. That can be said as the fx mod gx. If there is no remainder left, remainder is 0, that means there is perfect division, and gx divides fx. And fx, if gx has no divisor other than itself and 1, we say that it is prime polynomial. Just like a number, if you cannot factor the polynomial anymore, then it is called irreducible polynomial or prime polynomial. Okay? Now, let me just give you some examples of the polynomials that are reducible and that are not reducible. So, x plus 1, what are the factors of this? There is no other factor. Basically, x plus 1 is equal to x plus 1. You cannot factorize it anymore. So, this is a prime polynomial. Right? What if I wrote down x squared plus 1? Can you factor that? X squared plus 1 is equal to x plus 1 times x plus 1. Okay? In fact, when you could do it x squared plus 2x plus 1, 2x is 0, so you get x squared plus 1. So this is not a prime polynomial. What about x squared plus x plus 1? That's a prime polynomial. You can try it out, there is no factor. And so on and so forth. Alright. Now, just like you can do Euclid's algorithm for numbers, you can do Euclid's algorithm for polynomials. You take the big polynomial, divide by the small polynomial, get the remainder, then keep dividing until you get a 0 or a 1. Until you get a 0, yeah. If you get a 0, that means it is a perfect division and you got a common GCD, greatest common divisor. If it comes out 1, then you know there is an inverse, and so you can find the inverse as a polynomial. So here is an example of mod mx arithmetic. So everything here is done with respect to this polynomial. So when I ask you to add, let's say, two numbers, first number is, okay, by the way, every polynomial has a corresponding numeric representation whenever the Galois field is 2 raised to n. So for example, x is represented as 0, 1, 0. Why? Because the second power is 0, first power is 1, and the 0th power is 0. Coefficient is 0. So these are all the coefficients. If I gave you a number 1, 1, 1, that means x squared plus x plus 1. If I gave you 1, 1, 0, that is x squared plus x, and so on and so forth. So these numbers are same as these polynomials. Similarly, these numbers are same as the same polynomials here. Now, if you were to add these two polynomials or these two numbers, you will get something here. So let's try this one. I'm going to add x plus 1 and x plus 1. Okay? What do we get? 2x plus 2, which is 0. Right? If I add x plus 1 and x squared plus 1, I get x squared plus x. 1 cancels out. I can write this as a number. X square plus x is what? X square plus x is 110. So I could have written that 101 plus 011 is 110. So you can write it in binary numbers or you can write it in polynomials. Same thing. Now, addition is easy. Now multiplication. Multiplication may require you to do this long multiplication. But if you do that, then you get x plus 1 times x plus 1. You get x square plus 1. Just like we did there. If you do x square, multiply it to x square plus 1, you get x. Why x? So let's see why you get x. If you multiply x square to x square plus 1, we are multiplying x square to x square plus 1. You get x raised to 4 plus x square. Right? But x raised to 4 is more than our modular, this one. So that is modulus. Our modulus is x raised to 3. Right? So we have to reduce it to that, below that. So we just subtract x raised to 3 plus x plus 1, right? Plus x plus 1 times x. We have to subtract this quantity from this to bring it down below x raised to 3, right? So this is x raised to 4 plus x square plus x. You subtract that and you get x. Period. This cancels out, this cancels out. So that's the multiplication of those two. So we got an x there. Yeah.
Can you do another example of multiplication?
Yeah, let's do another example of multiplication. Choose one.
X squared plus x plus 1 times itself.
X squared. Can you say it again, please?
X squared plus x plus 1
X squared plus x plus 1 times
the same polynomial.
same polynomial. Okay. So we multiply this by longhand. Multiply by x square, we get x raised to 4 plus x raised to 3 plus x square. With x, we get x raised to 3 plus x square plus x. With 1, we get x square plus x plus 1. We add up, we get x raised to 4 plus x square plus 1. Good so far? Okay, now this is more than 3. Right? So we start subtracting. First thing we subtract is x raised to 4. Basically what you could do is you could just divide it by x raised to 3 plus x plus 1. When you divide it by long division, you must divide by that, you take x and you get x4 plus x square plus x. Cancels out, you get x plus 1 here. Right, now this is less than that, so this is remainder. So the answer is x plus 1. Let's see, x square plus 1 times x square plus 1 is x plus 1. You first multiply longhand and then you divide longhand to get the remainder. There is a lot of longhand division here in this chapter, actually, it turns out. All right, so here are some more examples. I think we probably did all of these anyway. Coefficients are 0 and 1. So if you want to multiply, if I could give you either the polynomial or the number. I could say, okay, multiply 101 and 111. If I give you numbers, you have choice of doing either way. You could do it by, at least in the 2 raised to n GF, actually you can do either way. You could just do by numbers or you could do it by polynomials. So let's just do this thing by numbers. Let's just, whatever we did a minute ago, let's just do it by numbers. So this, what is the number representation for this? That number is 111. right? And we are multiplying by this number, and that number is times 1, 1, 1, 1. Right? We could multiply it. First we take this one and we write down 1, 1, 1. Then we multiply by this second one. So we take 1, 1, 1. We multiply the third one. We do 1, 1, 1. We add up. We get 1, 0, 1, 0, 1. It's exactly that polynomial. Right? Now since this is more than our number 1, 1, 1, so we divide it by 1, 1, 1. First we go by 1 like that, and then we get 0, 1, 0, 0. Alright, and this is still more, so we divide by 1 more time, so we get 1, 1, 1. Subtract, you get 1, 1, 1. Get 1 more time, or we did make some mistake somewhere. So 1, 1, 0. 1, 0, 0, 1. 1, 1, 1. What did we do here? X cubed plus x plus 1. Oh, that was a different arithmetic. So, x cubed plus x plus 1. I wrote down, okay, alright, okay. So, that one we really have to do it by polynomial. So, because that's actually what we are doing here is we are doing multiplication of these two mod what I would call x cubed plus x plus 1. X cubed plus x plus 1 is 1, 0, 1, 1. Right? So we have to mod like that. So we have to do here 1, 0, 1, 1. And the whole division would be 1, 0, 1, 1. And you get 0, 0, 0, 1, 1, and that's it. So you can just work on the coefficients. Basically, that is just like working on the coefficient, not writing the x's. All right. So you have to know what are the coefficients, and then you have to know what is the modulus, which with respect to which we are defining these things. So that polynomial has to be kept into mind. All right. So addition, multiplication, and then reduction. Okay. Thank you very much. This is Michael, and you can basically reach him for any problems. Some people have problem with the logging in remote desktop, and so I don't know whether the permissions need to be set for them or whatever. So I just mentioned that. All right, so this is all clear, right? How to do multiplication, division, and all that. All right, so this is your homework. Determine the GCD of the following pairs of polynomials. So you have to find out the greatest common divisor of these two in GF11. All right. So basically, the numbers cannot be more than 11. So that means 11 is 0, and the rest of the rules we talked about. All right. And actually, I will show you the answer in a minute at the end of the slide so that you know exactly what the answers would look like. But anyway, so the last slide actually is that sometimes we want to generate everything by one element. So you could have a polynomial that generates all the members, all the polynomials of that set. So you could have polynomial z that generates all the polynomials, just like we saw in the number case. That would be a cyclic field or something like that. Cyclic group or cyclic field, when the elements can be generated just by power. That brings you to the end of this mathematical chapter. This is only half of the mathematics because the other half comes later, not basically in this lecture, but after one more chapter. Chapter 7 I think is another mathematics, but chapter 4 is done, and what we have learned is these 7 things. First of all, I think you learned is the tabular method for Euclid's algorithm, right? And if you do that, the advantage of that method is that you get the inverse figured out easily. Then we learned that there are groups and rings and fields and Galois fields, and the main thing is that these could be defined on the polynomial or could be defined on the numbers. Right? Everything that we talked about, addition, multiplication, division, subtraction, can be done in the polynomials or in the numbers. So we started first with the numbers and then we introduced the polynomials. So if you do numbers or either one, the group is an element and operation. You need an element and an operation that should satisfy the four properties. Abelian group would satisfy commutation. The rings will satisfy addition and multiplication. Fields will have commutation and the multiplication identity and inverse. Finite field will have finite number, and therefore they will have only two kinds, either p raised to n. Well, they have only one kind, p raised to n, which generally p is either equal to 2 or n equal to 1. See, that's another thing. I didn't mention that, but I haven't seen p squared or p cube or anything else. 2 cube, 2 raised to 5. So if p is 2, then we do all these powers. Otherwise, generally it is just prime number, power 1. And then in 2 raised to n, this should be 2 raised to n. GF 2 raised to n also form a field. Right? Okay. And so we already saw the homework.